Hello and good day, pre-algebra. Our task for this video is to kind of preview math packet number 6, go over some of its quirks and tricks, and get you started on answering the questions that it has. Note the due date. It is due January 26th. I posted it as a digital copy in Google Classroom on Monday. You will get a hard copy, a paper copy of it when you return to school on Monday the 11th. So you just want to wait until then to start to work on it, great. But if you wanted to get a jump or kind of start thinking through your process for some of these questions, hopefully you'll find this video helpful. So the first logic question we have: when you fold a square piece of paper, the resulting rectangle has a perimeter of 39 inches. What is the perimeter of the original square? Okay, so it's probably no secret that when you fold a square, you're going to get a rectangle, right? Because you're going from something that is has 4 equal sides. Okay, kind of fold it in half down the middle here, and it's going to become a rectangle, right, with the fold that you made right down there. Okay, so we know that the perimeter of our rectangle is 39 inches. And our job is to figure out what the perimeter of the original square, the original piece of paper was. Well, knowing that it's a square, there are a couple characteristics of squares. One of them being it has 4 right angles. But in this case, the more important one is that all 4 sides are the same length. So even though we don't know what those side lengths are, we can label each of them x. Okay, if x equals 2, then each side length is 2. If x equals 5, then each side length is 5, right? So they're all the same. And here's the thing to notice is that when we fold this piece of paper, the top and the bottom sides change, but the left and the right sides do not. In our folded piece of paper, I'll just change colors here. This is still x, that left vertical side is still x, and the right vertical side is still x. The top and the bottom sides are what changed. And so I want you to think about this now. If we started with a top side of x and folded that in half, what is the length of our new top side, or the top side of the rectangle, going to be? We started with x and folded it in half. Let's just play around with some numbers a little bit here. Let's say that our original x value is 20. If we fold that top side in half, the side length of that top rectangle will be 10, right? Because we'd have 10 here and 10 here, and this is the section that we end up with when we fold it. If that top, if x in the original square equals 50, that means we got 25 and 25. So the top side of our new rectangle is going to be 25. Because again, we just have that top side there. But since we don't have any numbers, we have to deal with x. And so if we start with a whole side length of x and fold it in half, the resulting side length is going to be half of x. And the same is going to be true for the bottom side, because in a rectangle, those opposite sides are congruent. So we have values for all 4 sides of that rectangle. We know what the perimeter is. It's 39. I'll let you finish it out. Use the information that you have here in that rectangle to solve for x, and then apply that value to the square to get the perimeter of the original square. Okay? Make sure you show all of your work. If you use the same method that I use here, obviously you need to have everything that I wrote down here, but also what you did after this, right, to get to the final answer. Next logic question. Tom has 4 different colored shirts: yellow, orange, blue, and red. He has 4 pairs of shorts: brown, black, green, and purple. How many different outfits can Tom make? So this is kind of a probability-based question, in that it's figuring out how many combinations of something. Okay, how many combinations of outfits, how many possible outfits exist with 4 shirts and 4 pairs of shorts. So what you might want to do here is you might want to start, let's say that Tom decides to wear the yellow shirt. What short colors could he match with that? Well, he could wear his brown shorts with his yellow shirt, or maybe he looks like a bee, wears his black shorts with his yellow shirt. Maybe he's a Packer fan, goes ahead and wears green shorts with the yellow shirt, or maybe he's a Vikings fan. Okay, wears the purple shorts with the yellow shirt. Right there, you've got 4 outfit options. Yellow shirt, brown short, black short, green shorts, purple shorts. Okay, what about if he doesn't choose yellow shirt, but he chooses orange? What shorts could he wear with that? Okay, one option here is to kind of lay out all of the different outfit combinations kind of in a web, like I have started there, and then count them all up. Okay, so that might be how you want to go that route. If you go a different route, again, just make sure you explain whether it's an equation or it's kind of a diagram picture like I have going on here, or it's words. Explain how you got to your answer. Next question. I bet it's a 5-card challenge. Indeed it is. We're familiar with these. Nothing really changes from packet to packet except for the cards that you can use. You are in pre-algebra, so you are going for those 15 points. A 10, a 2, a 7, a 3, and a 6 to make a 7. Okay. Next one, perimeter and area. Oh boy. So in our last packet, I believe we had a semicircle on top of a rectangle. Now we've got a semicircle and a triangle. So you're going to need to know both formulas for a semicircle and a triangle. For perimeter, we're looking for here, again, the outside of the figure. So in green here, I'll trace this side, which is given to you. This side, which is given to you as well. And that 7 there isn't going to be used for the perimeter because it's not on the outside of the figure, right? It's on the inside of the figure. So the rest of our perimeter is going to come from the outside of that semicircle. And if you remember, a circle, we don't really call it perimeter, but that distance around the outside is called the circumference. The circumference. And the formula for the circumference of a circle is pi. Oh, my pen just stopped writing here. Board just resetting. I think we're good. There we go. Pi times the diameter. The diameter being that segment that goes from one edge of the circle to the other and passes through the center. That's where that 7 comes in, right? That 7 is the diameter of that circle. But like we talked about in the last packet, this formula, pi times the diameter, gives us the circumference for the whole circle, but we don't have the whole circle. We only have half of the circle. So whatever value this equals, to get this half circumference here in green that we need for the perimeter of the figure, we're going to have to divide that by 2. Okay? Or multiply by 1/2. Either one. Multiply by half, divide by 2, it equals the same thing. Okay. For area now, we do need the area of a triangle, which is base times height divided by 2. And here, that divided by 2 is for a whole triangle. It's not that we want half of a triangle here. That is the formula for a whole triangle. Or you could use 1/2 times base times height. The area of a circle is pi times the radius squared. And remember here, the radius is the distance from the center of a circle to the edge. So this 7 being the diameter, the radius, which I'll draw in blue here, is just going to be half of that value. Right? So half of 7, which is gets squared and then multiplied by pi. But because we only have half of a circle, we only want half of the area that this formula gives us. This formula, pi r squared, is the area for an entire circle. We only have half of it. So again, we are going to divide this by 2. Okay? It can get kind of confusing because sometimes that dividing by 2 is part of the formula, such as for a triangle. For the circle, we're only doing that because we only have half a circle. If we only wanted 1/4 of a circle, we would divide by 4. If we wanted 1/3 of a circle, we would divide by 3. So it's not part of the original formula. We're using it in context for the figure that we have here. All right, very good. Onward and forward we go. Pattern blocks. I don't think I printed your packet out in color because I didn't think you needed it for anything else. So save some money. But your job here is to figure out what the pattern is, fill out the table, and then extend that pattern a little bit. I want to know how many blocks will be in the 12th figure. That answer will go down here on the answer line. So let's take a look at the pattern that we have developing. It's a little bit different pattern than we've had in previous packets. That's why I provided 5 figures here for you. But in figure 1, you've got 1 block. Figure 2 has 3. Figure 3 has 6. Figure 4 has 10. Figure 5 has 15. Okay. Take a look at those numbers. Take a look at the pattern. If you need to draw the 6th figure out, go ahead and do it. Hopefully you aren't just going to keep drawing these triangles all the way to the 12th figure. The goal of these pages is to find that pattern. Take a look. See what you can come up with. Next page, surface area. And today's shape, or this packet's focus shape, is a cone. So again here on these surface area pages, make sure you are drawing a net of the figure. That's like if we were if we had this figure made of paper and we unfolded it and laid it flat, what's it going to look like? Label the necessary sides and then find the area of that surface figure. And a cone's an interesting shape when you lay it out flat because it's got that kind of curved section to it, right? It does have a circular base, but then that curved part that makes that cone looks like this. It starts out being a triangle, but I can draw that better. Come on, I was in kindergarten. I can draw. No, it's not. No, okay. But then instead of a straight bottom side of this triangle, it's going to have a curved bottom side. And that's what gives us that cone shape. And then that circular base needs to be represented as well. All right, so that's the net of a cone. If you were to lay that out flat, take the wrapper off of your ice cream cone, lay it out flat, it's going to look kind of like that. Okay, so what are the important measurements here? Well, that 19, it's not the height of the cone. It's called the slant height. The height of the cone is a vertical line going from the tip straight down vertically to the base, but we don't use the height when calculating a surface area. That's why I didn't include that measurement here. So the sides of this triangle, triangular-ish shape here, are each going to be 19. And then I do provide you the radius of the circle as well. That's going to be 5. Okay, so the surface area is going to be the sum of the areas of these 2 parts that make up a cone. We already talked about the area of a circle. That is pi r squared. Okay, and the formula to find the area of this flat cone is pi times the radius, times the slant height. Okay, pi times the radius times the slant height, which we use as a cursive L. So you can find the areas of each of these shapes separately and then add them together. Or the official formula for the surface area of a cone is pi r squared plus pi r L, which is really the same thing as finding them each separately and then adding them together. It's written as one statement and meant to be solved as one fluid equation rather than 2 separate ones here. But either one's fine. Okay, either one's fine. And your surface area goes in that section on the answer line. Continuing with cones, we're now going to volume. The volume of a cone has a similar relationship to last packet or 2 packets ago, where we talked about pyramids. When we talked about pyramids, we said that a pyramid is as if it was cut from a cube, right? Because a pyramid has that square base, triangular sides. It's like we cut it out and removed it from a cube, which is why the formula for the volume of a pyramid is the same as the volume for a cube, base times width times height, we divide it by 3, because the pyramid is 1/3 of the cube that it would have come from. Similar with a cone and a cylinder. Okay, if you were to cut a cone and remove a cone from a cylinder, the volume of that cone is going to be 1/3 the volume of the cylinder it came from. So if you remember the formula for the volume of a cylinder, which is pi times the radius squared times the height, the volume of a cone is just going to be that divided by 3. Let me rewrite this so it's a little bit cleaner. Pi times the radius squared times the height, there's your cylinder. Divide that by 3, and you have the volume of your cone. Okay? So in this case, the calculation that we'll perform to find the volume of this cone is pi times 7 squared, the radius squared, times the height, which is 18. And I mentioned it in the surface area page. Notice that that height, that 18, is a vertical line coming from the top of the cone straight down, making a right angle with the base. I'm not giving you the slant height here because we're not going to use it. I don't want to confuse you too much. Right? Slant height for surface area, the height of the cone, the vertical height for a volume. But anyway, pi times 7 squared times 18, divide that by 3. And let me get my calculating tool here to do some quick maths. Pi times 49, which is 7 squared times 18, divide that by 3, and we get 923.63. And there's no units provided, so we'll, oops, not units squared, so we'll call it units cubed. Okay? There's no measurement provided, we just go with units. Then, your job, being in pre-algebra, says a cone has a volume of 131 cubic meters with a radius of 5 meters. What is the cone's height? So in this case, we're working with that formula for the volume of a cone. The volume is pi times the radius squared times the height divided by 3. I'm giving you the value of the radius, and I'm giving you the volume. So we can replace this capital V for the volume with 131. We can replace the radius with 5, and we're solving for the height. Okay, so this is equation solving, which is the unit that we just completed, but it's a little bit more challenging than the equations that you had in the unit, but we're still going to be using opposite operations here. Okay, so play with this a little bit. What value for the height is going to get you that total volume of 131? And if you need help, then of course you can come and seek me out. Next question, next page. Math exploration, the Jordan curve theorem. The figure on the right is an example of the Jordan curve theorem. Notice how the gray section of the figure is enclosed and connected. If you want to think about this as like being inside the figure and outside the figure, anywhere in this shaded, this gray section here, if I'm trapped, if I'm walking through here, I'm not getting out, right? There are walls all around me. Okay, no way out. I'm kind of inside the figure. I'm enclosed. I'm not getting out. Right. So it says, notice how the gray section of the figure is enclosed and connected, meaning you can get from any point in the gray section to any other point in the gray section without leaving it. The same is true for the white section. Okay, the white section is kind of the outside of the figure, meaning that if I'm here, I can just get out by taking a hard right as I walk forward, okay, and exit. Okay, so inside and outside. Whoop, hold on. I think There we go. How do I get rid of this? There, okay. You can also consider the gray section to be inside of the figure and the white to be outside. The Jordan curve theorem simply states that a closed curve divides a plane into an inside and an outside. Okay? And your job here is for each figure below, determine if the point is on the inside or the outside of the figure. Meaning that if I gave you a point in this figure here, can you leave it? No. Therefore, it's on the inside. If I gave you a point right here, can you leave the figure? Yes. Therefore, it's on the outside. So for this first one, your point is here. Is that on the inside or the outside of the figure? Can you leave the figure? Well, let's see. Let's kind of explore. Walking around. No, can't go. No. No, this is no, I'm trapped. Ah, I'm on the inside. So for that first one, the given point is on the inside of the figure. Okay. Second one, third one, fourth one, fifth one. The points get a little bit more challenging there, right? And then this section down here is my gift to you in the spirit of Christmas. Here's a hint. If you're having trouble, the Jordan curve theorem also states that you can determine inside or outside by imagining a straight line going from the point to beyond the boundary of the figure. So it's like I took a straight line from this point and just went out. Okay? Straight line out. If the line crosses the curve an even number of times, the point is outside. If an odd number of times, the point is inside. So what I want to do here is I want to look at my point and decide how many times does this cross through a line of the figure. 1, 2, 3. An odd number of times, therefore the point is inside, which is the same answer that we got here. Okay? Let's draw a different line through. Let's put one, let's go, only crosses it once. 1 is odd, therefore we know the point is inside the figure. So for the rest of these, where it can be kind of difficult to trace this point out, draw a line. How many times does that line pass through the figure? Maybe it would be easier just to trace it in or out. Okay, but that is the Jordan curve theorem. The Jordan curve theorem allows you to determine whether something is inside or outside of a figure. Last but not least, the polynomial section. You've got 8 of them provided, and again, to point this out, the way that these polynomials appear is exactly how they appear in the figure itself. There's no turning, no twisting, no flipping, rotating, anything like that. The way they appear is exactly the position they are in the figure. So your job is to figure out where they all are and identify them so that I can tell. There you go. That's math packet number 6. Like I said, it is due on January 26th. So if you have questions, please do come and see me. You can turn it in early for me to check over. You'll get your paper copy on Monday, and hopefully this video helped you figure some things out. So with that, I bid you adieu. Have a great day. Don't forget to like and subscribe. I'll talk to you later.